Welcome to part 4 of 6. I'm going to try and fit the next 2 pages into hopefully less than 15 minutes. We'll see how we go. Okay, see, a skateboard park has a mound that is 8 meters high. Okay, so they want H at the point where the horizontal distance from a fixed point P is in X meters. So we're talking in terms of X, so we want H of X, and here's our point P. The mound can be modelled by H. Okay, they've already got an equation. What is a maximum height of the mound? Okay, maximum. They want us to differentiate, and it's going to be at the turning point. So where H dash of X is going to equal 0. Okay. So let's get on to it. H of X at H dashed of X will equal negative X plus 3. Okay, so 0.5 is the same as half. Multiply half by 2, you're going to get 1, but it's a negative number, so be careful with your negatives. Okay, so we've got this. 0 is equal to negative X plus 3. X is going to equal 3. So max height at X equals 3. They want to know the height, so that means we need to use the original equation. So height is going to be negative a half times 3 squared, which is going to be 4.5 minus 4.5 plus 3 times 3 minus 1.5. Which should give us 3 meters. Minus plus, that's 9. Yep, 3 meters. Okay. A ramp is up the side of the mound. Sorry. The side of the mound is a tangent to the mound. Okay, so straight, it's linear, like all tangents. The ramp can be modelled by the function this. Okay, so that's the ramp. Use calculus to find the vertical distance below the top of the mound where the ramp will meet the mound. So here we already know our max height is 3 meters. They want to know the difference between the top and here. Okay. So we need to find the height here. Okay, so we have already differentiated over here. So we've got our gradient function up here. The fact that we've got minus c here doesn't actually matter, because what we really need is this bit here anyway, because we don't know where it meets with the equation. All we know is that the gradient is given here, and the gradient of the tangent must be equal to the gradient of the curve at the same point where it meets. So because of this, what we can do is plug the gradient into the gradient equation. So we've got, that's a positive, 0.5 is equal to negative x plus 3. So that means where it meets, x is equal to 2.5. So just finding the height. The height at that point is, let's plug it into the original equation, which is -0.5, 2.5 squared, 3x minus 1.5, 3x. Yep. Okay. Which should give us 2.875, I guess. 2.875. Okay, so that's the height here. But they want to know the distance below the top. Not the distance from the point P up. Okay, so this gives us the distance from the vertical distance from point P. We don't want that. We want below the top. So if we say 3 minus 2.875 should give us 0.125. Top of the mound. Okay. Okay. The height meters of a skateboard path at a horizontal distance r meters from another point Q so horizontal, so distance wise, distance r meters from another point Q can be modeled by the function this. There's a height regulation that requires no part of the skateboard path to be more than 3 meters above ground. Okay, so it's still height. Fully describe this curve, including its turning points, and state whether or not the skateboard path complies with the height regulation. Okay, this is definitely an excellence question. Not that should mean anything. So we know that it is a cubic because the highest power is to the power of 3. It's a positive cubic. So height-wise, it's going to look something kind of like this. Maybe stretched out further. Most probably stretched out further because it's divided by 3. So what we need to do is find the turning points. And when we talk about turning points, it means that we need to differentiate it. And whether or not the skateboard path complies with the height regulation. So at this turning point, we need to make sure it does not go more than 3 meters. Okay? Must not be greater than 3 meters. So let's get started on doing the calculus part, shall we? So h dashed of r, or you can say dh dr, okay, differentiating with respect to r, is going to be r squared minus 4r plus 3. Okay, so for the turning points, we need our gradient function to equal 0, because the gradient is 0 at the turning points. We've got r squared minus 4r plus 3 negative, so 1 and 3. R minus 1, r minus 3 is going to give us 1 and 3. Reading left to right, smaller numbers come first, so that is going to be where r equals 1, and this is going to be where r equals 3. The height at these points let's see. It's going to be 1/3 minus 1 squared is going to be 1 minus 2. 3 times r, 3 times 1 is 3. 4/3. That's 4/3. How much space do we have? Alright, let's start working across the page. When r is 3, height is going to be 3 cubed over 3 is just going to be the same as 3 squared. Two times, well, we've got 3 squared. 2 times 9 is 18. 3 3s are 9. Is it a plus? So that should equal 0. Because these two equal 18. Okay. Okay, at this point here, does that exceed 3 meters? No. So this is the local max, and it is smaller than 3 meters. Therefore, within restriction. Okay. Now it's a positive one. See, and it says that the maximum distance it goes from this point is 3.5 meters. So let's have a look at 3.5. So height at 3.5, because it's going back up. Times 3.5 squared plus 3 times which should be 0.29166, blah blah blah, if you use your calculator. I'm going to round it to 2 decimal places, which is also less than 3 meters. Positive cubic, therefore from above, working no points exceed regulations. Whoops. Let's see if we can write this. Regulations with local maximum max turning point at 1 meter away from, was it from Q? From point Q? Reaching height of only 1 1/3. 0.33 meters and local minimum turning point at 3 meters away from Q. Was about to write question, oh dear. Reaching height of 0 meters. Okay, and we're done. Thanks for watching.